Hello again. This is the solving of the monkey free response problem that I gave you guys as a sample. Now, to be perfectly honest, I think this might just be the hardest one that we had in there, or at least it's the lengthiest in terms of at least this one part here that's only worth 6 points. Now, first of all, on the above right diagram, draw and label all the forces acting on the monkey. Do not resolve the forces into components, but do indicate their directions. Fine. So basically, we're recreating this. So we have something going up in this direction. This is going to be T sub B, and it's nice to put it into words. Now, they said indicate directions, so that's going to be at 60 degrees above the horizontal direction. I'm going to call that X. This is the tension in vine B. All right. Over here, we're going to have T sub A. Now, I do not expect T sub A to be as big. Now, they didn't say draw it to scale. Indicating some scale, if you are aware of it, is useful. Had you just made it equally sized, it wouldn't have counted against you. This is going to be T sub A. Tension in vine A, just to be perfectly clear, and the angle here is going to be 30 degrees, and then downward, vertically this much, so about yay, is the weight, W, the weight of the monkey that we will use a W for. Okay, here's where life gets big and ugly. Determine the tension in vine B while the monkey is at rest. While I get a text message, which I will check. My kids want me home soon. I will text them as soon as we're done with this. The tension in vine B, all right, we know that he's in equilibrium. And the fact that he's in equilibrium, the fact that the sum of the forces are equal to 0, mean that the sum of the forces in the x direction are equal to 0. And of course, the sum of the forces in the y direction are equal to 0. So we're going to get two sets of equations for our two unknowns, both of the tensions, and therefore we can solve it for one of the values. In the x direction, we have tension A sub x equals tension B sub x. How hard this one is pulling to the left is equal to how hard this one is pulling to the right. How far this goes to the left equals how far that one goes to the right. And of course, that is the adjacent side over here, so that's always going to be cosine. So we're going to have T sub A times cosine. If we wanted to call it theta A, we could. Why not? We'll go with theta A equals T sub B, the tension in vine B, times the cosine of theta B. We're trying to solve this whole thing for the tension in B, so I'm going to try to cancel out the tension in A, so I'm solving this equation for it. So tension A is equal to tension B times cosine theta B divided by cosine theta A. I'm just going to substitute that over here. Cosine theta B divided by cosine theta A. All right. Now we do the y's, and then it's substitution time. Okay, in the y direction, the upward forces equal the downward forces. Fine, so let's say T sub A in the y direction plus T sub B in the y direction equals the downward force W. That means that we've got T sub A times the sines this time, sine of theta A plus T sub B times the sine of theta b equaling w. We are now going to make our substitution from here over to here. So t sub a gets substituted, and we've got t sub b times that mess, cosine theta b divided by cosine theta a times still sine theta a plus t sub b sine theta b, all equaling w. All right, at this point, you should do something like continued on back. All right, I'm going to get out a blank piece of paper so that we can wrap this up without flipping the page over. So move this up a smidge. All right, here's the back of the paper, just because I don't want to lose track of what the heck I'm doing. All right, first I'm going to clean this up a little bit. That is t sub b. I have theta a twice, and that's sine over cosine, so that's tangent. So that's t sub b times the tangent of theta a times the cosine of theta b plus t b sine theta b equals w. Pull the t sub b's out. Okay, so my tension in the b, my tension in vine b is tangent of theta a times the cosine of theta b plus the sine of theta b equaling w, which now I'm going to substitute as mg. All right, we can leave it as this big ugly mess right now and let our calculators sort it out a little later on, or we can solve for that in-between step and say that that all this junk is equal to some numeric value. It doesn't really matter. I'm going to just leave it in variable format. So mg divided by all this mess, tangent of theta a, cosine of theta b plus the sine of theta b. Now I'm going to substitute in some numbers. M was 5.0 kilograms. G, we've been using 10 just to make our lives easy. And I really shouldn't say 10.0. I'm going to leave it as 10. 10 meters per second squared. It really is basically 2 sig figs at most. On the bottom, tangent of theta a. I'm going to have to write down tangent of 30 degrees times the cosine of 60 degrees plus the sine of b, so that's 60 degrees. Okay, a little bit of calculator work for simplifying out the bottom. 30 times tangent plus 60 cosine, not plus. Okay, tangent of 30 times the cosine of 60 plus the sine of 60 equals 1.15. So I end up with 50 divided by 1.15. Divided by 1.15, and I end up with 43.5, and it's kind of asking for a lot. That's as far as I would push my significant digits around here, is going to 3. I think we really should be only going to 2 here, but they actually won't dock you points for this. 43.5 newtons. All right, so I'm going to Okay, and so this is the back of my paper. I'm going to get rid of that right now. So I'm back over here. I have transferred the answer over to the other side, and that does seem about right. When I was trying to eyeball this thing, and so that this thing was that one plus that one, this one does look like it's going to need to be longer than that guy up there. So I'm believing in that general magnitude there. It sounds about right. I'm not going to look at that. Okay. All right, now the monkey's going to do something weird. The monkey's going to release vine A and swing on vine B. Neglecting air resistance. This is conservation of energy. So he is going from here down to here, where this is 60 degrees. This is 10 meters. And so he is going from this initial position here, where I'm going to say the potential energy initial is going to be equal to the kinetic energy final. First, I got to figure out what that drop is. From here to here is going to be h. First, I'm going to find y over here on this side. And y is going to be equal to 10 meters. Opposite side from the 60, so that's sine. So, yeah, that's sine. Sine of 60 degrees. So the value of y is 10 times 60 sine 8.66. I'm just going to call that 8.7 meters. So h is therefore equal to 1.3 meters, because this is 10 all the way down to here, minus the 8.7. So my potential energy initial equals my kinetic energy final. That's mgh initial equals 1/2 mv final squared. Mass cancels out. V final is equal to 2 times g times h initial square rooted. So we've got the square root of 2 times 10 meters per second squared times 1.3 meters square rooted. So my final velocity, the velocity at the bottom, 1.3 times 20, and then square rooted is 5.099, so we're going to call that 5.1 meters per second. All right, lastly, determine the tension in vine B as the monkey passes through the lowest point of its first swing. This should sound familiar. This is a apparent weight problem. So it's going to be the force that's causing it to move in the circle is equal to the mass times g plus or minus the centripetal force at the bottom. You always feel heavier, so it's always plus the centripetal acceleration. So that means mass times g plus v squared over r. If you wanted to call that v final because it wasn't the last one, that would be fine, but it's not necessary. Just like I don't have to call this t sub b, I could just call it t. Just plugging in my numbers here, I've got 5.0 kilograms. I've got 10 meters per second squared plus v squared, v being 5.1 meters per second. Got to square that, divided by my radius of 10 meters, okay, which again is why we're not going nuts on the significant digits. So my tension in the vine, 5.1 squared is 26.01 divided by 10. We get 2.6. 2.6 plus 10, so we got 12.6 times 5, and we end up with a tension of 63 newtons, and I believe that it should definitely have more tension at the bottom of a swing than when it was holding up part of the weight. Okay, sorry that one was so long. If you looked into this one, I hope you got your points there. Okay. Again, that was 2 points for the 3 forces, 6 points if you could pull this guy off here, 4 points for your final velocity, and 3 points for the tension at the bottom of the swing.